So in this one, we're going to be looking at functions and determining where they are discontinuous, and they're very, very quick. So we're going to start with a rational function, and then move on to a piecewise, and then a trig function, so that we've represented all three. So the first one, with rational functions, you know that denominators cannot be equal to 0. That is where we get wholes, removable discontinuity, and vertical asymptotes, which is an infinite discontinuity. So if you set the denominator not equal to 0, right, we get x cannot be 4. So the following point is discontinuous. The following function is discontinuous at x equals 4. It has an infinite. As you can see from the graph. So we're coming in, and then it goes straight down to negative infinity, and then I have to start up here and then come back down. That is an infinite discontinuity at x equals 4 from our graph that you can see. You can also tell it's not a whole because this did not cancel. So if there was an x plus 4 on the top and it canceled, it would have become a whole, which would be a removable discontinuity. And then how does this not fit our definition? Well, you can see that f of a is not defined. So f of 4 is not defined. It's actually undefined. So you could just check off number 1. It fails. Number 1, that tells us it's discontinuous at x equals 4. The limit also does not exist because it goes down to negative infinity and up to positive infinity. Okay, piecewise function. So with piecewise function, we're looking at, again, do you have to pick up your pencil? So I'm coming in here, then I have to pick up my pencil to go here. So we know we're going to have a point of discontinuity based on the graph. Well, looking at it, we know that that's probably exactly where our x is equal to 3, because this is a piecewise defined function. So you're getting a graph to the left and a graph to the right. So all you have to do to tell if that is a point of discontinuity is plug that 3 in. So 3 plus 2 is equal to 5. And 2 times 3 is equal to 6. So coming in on your graph, that's x is less than 3, we're going to be coming into 6. So at 3, we're going to get 6, and that is a closed dot. Down here is an open dot because it's the greater than. But if you were to plug in 3, we would get 5. See, this is for our x is greater than 3, and this is for our x is less than 3, or equal to. These two here. And so we know since they're not the same point, we're going to have a point of discontinuity. So that means it is discontinuous at x equals 3, and it is a jump discontinuity. And again, to show this, it is defined at that value. You can see that at 3 we get 6, so you cannot use a to disprove it. Number 1. But you can use number 2. So we know the limit as x approaches 3 of f of 3 does not exist. And so number 2 fails. So there you have it. So if you use these values, it tells you where it is. So it's discontinuous at x equals 3 because coming in from the left and the right, our limits are different. So the limit as x approaches 3 from the negative would be 6, and the limit as x approaches 3 from the right would be 5. So the limit as x approaches 3 from the left of our f of x is equal to 6. And the limit as x approaches 3 from the right of f of x is equal to 5. Therefore, the limit does not exist because they are not the same value, which means it's this point of discontinuity. So that's how you could prove that that one is discontinuous. All right, on to tangents. So we know with tangents that there is points of undefined values. And so with tangent, you want to think about what it normally is. So with tangent, it's always going to be x equals pi over 2, and it's based on its period, right? It's where it starts. So it's normally at negative pi over 2 to pi over 2. If you put numbers in there, they're going to have that repeatable vertical asymptotes. So you want to put plus pi k, which is tangent's period. So that is where we have our discontinuity. So it is discontinuous, because x cannot equal those, at x equals pi over 2 plus pi k, where k is an integer. And what type of discontinuity? That is an infinite discontinuity. And so again, here's my question. Think about it real quick before I tell you the answer. Which of these on our checklist disprove the continuity? So they show that it is not continuous. They show that it is discontinuous. Is it 1, 2, or 3? Exactly, you could use 1 or 2. Since they both go to infinity and negative infinity, the limit doesn't exist. But I like number 1's checklist. This one's where it fails, because f of pi over 2 plus pi k, right, is undefined. So it is not defined, so it fails number 1. Okay, so here's a problem for you I want you to try. And so what I want you to do is tell me, all I need from you is, where is this one discontinuous? And what types of discontinuity do we have? And then you're going to use the left and right limits to show why. Okay? Or you're going to show that the value is not defined or that it does not exist. So hit pause and give it a shot. Okay, so we're going to now break this down. So the first thing you always do with rational functions is factor them, because that's going to tell us whether it's removable or not. So we end up with this. So if you cancel this, immediately that x minus 2 over x minus 2 means we have a whole at whatever that was. So that would be 2. So at x equals 2, if I were to plug 2 into here, I'd get 0 and 0. So it's at x equals 2. Whatever's left is your vertical asymptote. So this one now says that x cannot be negative 2. So that is your infinite. And this is your removable. So whatever cancels is a removable discontinuity because it's a whole. And whatever is not canceled, that is your infinite discontinuity. So, but no matter what, we have something that is discontinuous. So it's discontinuous at x equals negative 2 and 2. And the negative 2 is an infinite discontinuity. So x equals negative 2 is an infinite discontinuity. And the x equals 2 is a removable. So here's the thing. With an infinite discontinuity, you can use your limits to show that they don't exist. But it's easier with the infinite just to show that the value is not defined. So with both of them, it's just easier to say that they are not defined. So for number 1, it fails for both x equals negative 2 and 2. F of 2 is not defined. It's undefined. Let me try that again. Defined. And f of negative 2 is also not defined. So going back to our checklist, if this is not defined, it's not continuous. In order for it to be continuous, all 3 have to be true. So for the limit, here we go. It fails number 1 right off the bat. And there you have it. Thank you.